The Spanning Tree Protocol, STP, is a network protocol designed to create a loop-free logical topology for Ethernet networks and prevent bridge loops and the resulting broadcast radiation. This protocol establishes a spanning tree that defines the relationship between nodes in a network of connected Layer 2 bridges, enabling a single active path between any two network nodes. Invented by Radia Perlman while at Digital Equipment Corporation, STP ensures fault tolerance by allowing backup links in case of link failures. Rapid Spanning Tree Protocol, RSTP, introduced by the IEE in 2001 as 802.1W, enhances convergence behaviors and bridge port roles, enabling faster recovery from network changes or failures while remaining backward compatible with STP. The functionalities of STP, RSTP, and Multiple Spanning Tree Protocol, MSTP, have been incorporated into IEE 802.1Q 2014. Although STP is still utilized today, its primary role in modern networks is typically for loop protection rather than fault tolerance. To provide fault tolerance and increase link capacity, networks commonly employ link aggregation protocols like LACP, which bond multiple links. STP maintains network stability by designating bridge ports as root ports, designated ports, or blocked ports to establish a preferred link between switches and prevent switching loops. Bridges communicate via Bridge Protocol Data Units, BPDUs, to determine the best path to the root bridge based on path cost calculated from link bandwidth. The STP path cost is determined by the bandwidth of each link, with faster speeds leading to adjusted default values to distinguish between different link speeds. Ports in a switched LAN undergo various states such as blocking, listening, learning, and forwarding as they process BPDUs and populate MAC tables. Topology changes are communicated through topology change notifications, TCNs, to inform switches of port changes and rapidly age out forwarding table entries. Before configuring STP, careful network topology planning is essential, including enabling STP on all switches, selecting the root bridge, and configuring switches to ensure consistent operation. The root bridge is chosen based on the lowest bridge ID, which is a concatenation of the bridge priority and MAC address. Path selection to the root bridge considers factors like lowest root bridge ID, cost, sender bridge ID, and sender port ID, with tiebreakers used to determine root ports and designated ports in the network. The algorithm for determining the spanning tree relies on the exchange of Bridge Protocol Data Units, BPDUs, amongst bridges in a network. These BPDUs carry vital information such as bridge IDs, root bridge identification, and route path costs to assist bridges in computing their port roles effectively. Regular exchange of BPDUs allows switches to adjust to network modifications promptly. Rapid Spanning Tree Protocol, RSTP, was developed to enhance the convergence speed of spanning trees, especially during topology changes, ensuring faster transition of ports to the forwarding state when needed. RSTP introduces new port roles like root, designated, alternate, backup, and disabled to accelerate convergence following link failures, compared to the longer response time of traditional STP. By streamlining port states into discarding, learning, and forwarding, RSTP greatly simplifies and speeds up the process of spanning tree computation after network alterations. Furthermore, RSTP operates by swiftly identifying root switch failures within a short interval of 6 seconds, avoiding unnecessary delays. It categorizes ports as edge ports for immediate activation in LANs without other bridges, ensuring quick response times for hosts connecting to the network. RSTP is capable of adjusting port statuses dynamically based on the presence of BPDUs, thus adapting to changing network conditions efficiently. The protocol also distinguishes between different types of links, classifying them as point-to-point or shared connections to optimize convergence. Notably, RSTP utilizes a proposal agreement mechanism where switches negotiate port roles swiftly by proposing superior spanning tree information to each other, allowing for rapid forwarding state transitions without the usual listening, learning phases. This cascade effect among designated bridges facilitates faster convergence times, a key advantage of RSTP over traditional STP methods. Unlike STP, RSTP employs a proactive approach towards incoming BPDUs and ensures efficient backup port management to prevent disruptions or timeouts in the network. It reverts to standard STP if legacy BPDU versions are detected, guaranteeing backward compatibility with older bridge configurations. Overall, RSTP's streamlined operational details and port role assignments significantly improve the network's responsiveness to topology changes and enhance the overall efficiency of spanning tree computations.